Welcome back, y'all. We are in example 5. We're going to build another circuit. This one has a little bit different topology. Another way to think about that is the connectivity of this behaves a little differently. In this case, we see the wiring diagram right here. We have a single 5-volt voltage source. We have 1K resistors. There's one, there's two of them. And then we have two orange jumper wires, which are 0.3 inches long. The schematic associated with this circuit is seen right next to it. Notice that we have reversed the polarity, so the positive lead, the red lead of our voltage source, is going to be on the bottom and the black lead is on top. Wanted to do that so that we could see the connection between the schematic and the actual source that we attach. In this case, we're going to need the following items that you see laid out: a half-size breadboard, two orange jumper wires, two 1K resistors. This is not correct. This should be, so that's a typo, I'm sorry. I need a voltage source, of course, and then I need a fully charged battery. Let's go ahead and build this circuit. So the first thing that we're going to do is disconnect the battery. That's already done for us. Next thing we're going to do is connect the jumper between E10 and F10. Push straight down so that it goes into the little clamps. Same things here. I'm going to grab that orange jumper, put it between E20 and F20, and that makes all of these points, which are connected underneath inside the breadboard, now they are electrically connected to this one. So it's a single piece of wire that runs all the way from A10 to J10, and the same thing is true A20 through J20. After that, we're going to insert resistor 1 across D10 and D20. So that now gives us a resistor across that set. And then the same thing is true over here. We're going to put this one between it looks like I did H. Funny thing though, it doesn't even matter if I do H, I, or J. As long as the connection is one side of the resistor up here and the other lead down there, I'll be fine. In this case, I'm going to take that's incorrect. I'm going to take the red lead and attach it to A20. And I'm going to take the black lead and attach it to A10. And then now I have my circuit set up. So the wiring diagram that I see on screen matches identically what's happening in the actual circuit. Next thing we're going to do is make some measurements here. Let's go ahead and transition to the measurement process. Here we go. Here we're all set up. The battery's connected. The circuit is live. We are going to make measurements. Each circuit element has two variables, so there's a total of 2, 4, 6 variables that we're going to measure. In this case, we're going to define the voltage drop across each element and the current running through. We recall in our previous discussion, I think it was example 1, that we said that anytime we are defining a voltage reference for a voltage source, the reference direction for the voltage drop across that source is going to be in the same direction as the actual source is connected. In other words, I'm going to connect my red lead to where the positive sign of that voltage is and the black lead to where the negative sign, so that measurement is always positive. The moment that I do that, we have said previously that the corresponding current variable will go from red to black or from positive to negative, and we're going to call that IV1. So VV1 is the voltage drop across that voltage source. Ideally, we say that's 5 volts. We've been seeing in these different experiments that it ends up being not exactly 5 volts. IV1 is going to be the current running through that voltage source, and the reference current is going to be in the direction from positive to negative. Next thing we're going to do is define a priori. It doesn't really matter what order we do it in. Perhaps we'll say the same polarity works, so we'll claim that the negative sign is on top and the positive sign is on bottom, and then we'll define the voltage drop across resistor 1, which we'll say R1. So VR1 is the voltage drop across that resistor. The moment we define that, we know that the corresponding current through that resistor we will define from the positive to the negative, and we'll call that IR1. Last element that we're working with here is the second resistor. And in this case, why don't we just switch the order? The reason that I want to do this is I want to show you that it doesn't really matter how we assign these to begin with. What matters is that we track our reference. So in this case, we'll call the voltage drop across resistor 2 VR2. We'll assume the polarity goes from the top to the bottom. The moment that we do this, we know we have another current variable that goes from the red to the black, and we'll call that the current running through the second resistor. Let's go ahead and measure each of those. In the modeling paradigm, we're going to adopt the linear algebra. Remember that all of this is to lead up to the construction of a linear systems problem. When we do that, we're going to order it first by focusing on the resistors, then the voltage source, then the current. So in the measurement process, let's go ahead and start with the resistors, which is why they're listed in that order here. First things first, we see that the first resistor, we're going to attach the red on the top and the black on the bottom. And we see that the voltage drop across that resistor is positive 4.96 volts. Next thing we're going to do is to measure the voltage drop across resistor 2. In this case, we see that we attach the black on the bottom and the red on the top. And indeed, that has a negative 4.96. Finally, we're going to go ahead and measure the voltage drop across our voltage source. In this case, we attach the positive lead on the bottom and the negative lead on top, and we get a positive 4.96 volts. With reference to these chosen directions, we have these measurements, all identical. This has to do with the behavior of what we call parallel circuit elements, which we'll talk about later in this video. Next thing we're going to do is go ahead and translate our digital multimeter into an ammeter functionality. So in this situation, I switch it over to milliamps. From here, notice that I'm going to want, when I measure this, I'm going to want to connect the red to black in that polarity, but I'm going to have to do so to measure the current. So in this case, why don't we start with the current running through resistor 1. So I'm going to go ahead and connect the black here, and then I'll connect the red on the bottom. So look, it goes from red to black. Do you see that? That as it goes to red to black. And we have a current measurement through resistor 1 of positive 5.14 milliamps. It's the first one. We'll go ahead and reconnect this circuit. So I go ahead and put this thing back to where it was, or something close to it. Next thing we're going to do is measure the current running through resistor 2. So in this situation, I'll go ahead and drop that one. I want the red on the top and the black on the bottom. So it looks like a negative 5.14 milliamps. And then the last thing that I want to do is figure out how much current is running through the voltage source. So I reconnect this thing. Let's go ahead and measure this portion of current. So current's going to be running through this in this reference direction this way. We're going to insert our ammeter on this portion, and we're going to do so red on top followed by black. So red and black, because that's the polarity, right? Red to black, and it's in that reference. So here we'll go ahead and take this lead of that voltage source out. We'll connect the black on top, and the question is how much current is running from the red to the black. And it looks like 10.26 with a negative 10.26 milliamps. And notice these are almost the sum of each other. I'm not talking about the signs, I'm talking about the magnitude. Anytime we're summing things like that, that's called linearity. Linear algebra means summing stuff. Kind of exciting, right? Boop, boop, boom. So it's not exactly correct. It should be 0.28 when we sum those. But I wanted to show, like, this is the difference between theory and practice. In practice, there's always some interesting stuff going on. In this example, we built this circuit seen in the wiring diagram, and that corresponded with the ideal schematic down here. The measurements that we had for each individual circuit variable, there's 6 of them, we saw here, and we see this really interesting pattern that the voltage drop across each of these elements are identical in magnitude but have differing signs. I wanted to show why that's true by introducing some ideas that we're going to dive much deeper into in future videos. This has to do with the concept of nodes. In order to get our head around concept of nodes, what I want to talk about is the idea of wires. Notice that in this case, we're going to use blue to represent a single wire in terms of connectivity without elements. So everything on the bottom here is connected as a single wire. Now in the actual circuit that we built, of course, you could argue, hey, that's not a single wire. That's 1, 2, 3, 4, 5, 6 different pieces. But electrically speaking, with what's actually happening with the electron flow, it doesn't distinguish. Literally, electrons can flow freely through this, or current can flow freely through those different pieces of wires as if they were the same thing. And in the schematic, that's exactly what we see here. All of these pieces are identical. Doesn't matter where I connect it, they're all the same. Similarly, when I look up here, we see that all of these pieces of wires actually represent the exact same wire. Now, when we measure voltages, remember what we did is we connected one lead of my multimeter to one side and one lead to the other side, and the difference in potential was the measurement of voltage across that. But the very, very interesting claim about this is because this point of wire, electrically speaking, has the identical behavior as this point of wire or this point of wire, it doesn't matter where I connect those particular leads, the measurement's going to be the same. And that is why when we looked at these measurements, if I connect my two leads on this side, that is identical to connecting my two leads on that side. In other words, the voltage drop across this voltage source is the same as the voltage drop across this resistor. Now, the magnitude of that voltage source is identical over here because look at, we said that those wires have the same drop. In fact, if I were to move the red lead to any point along that wire, I would get the same measurement, and we can do that really quickly. Check this out. If I were to move, let's say I take the red lead down here and I put the black lead on the other side of that resistor, notice I get 4.96 volts. If I put the red lead in the middle and the black lead over here, 4.96 volts. And the reason that it's always 4.96 volt is, electrically speaking, those pieces of wires are the same component. It's literally the exact same volt charge differential that I'm measuring. That is why these measurements align so nicely. The negative comes from the fact that each measurement has not only a magnitude but a sign, and in this one I'm switching the polarity, so the magnitude is the same, but we swap the sign to say, hey, in my measurement tool I actually measured it in the reverse order. Of course, we also have Ohm's law happening here. Ohm's law says that V equals IR. If I multiply this number by 1,000 ohms, I get something that looks like that, and vice versa. This example 5 leads to a very, very powerful idea in electrical engineering, which is the concept of parallel elements. Parallel elements share the same pieces of wires across the body of the element. In other words, we're going to call those nodes. So when we think about a single connective piece of wire, that whole thing is a node. So notice that these three elements have one node on the bottom, one node on the top, and they're identical to each other. Those are in parallel. And the way I kind of think about this is when I put elements in parallel, they're literally side to side to each other. That's a set of parallel elements. It doesn't really matter. That could be a voltage source, it could be a resistor, it could be a current source. It doesn't really matter. The point of the matter is all the wire up top here is the same individual piece of wire, and all the wire on the bottom is the same piece of wire. Those are in parallel. Parallel elements have the same voltage drop across the leads. The voltage drop across that element is identical to the voltage drop across that element, is identical to the voltage drop across the third element, because when we measure voltage drops, we put one lead of our multimeter on one side, the other on the other side. Those sides are the same. So those three measurements are identical. That concludes our work on this example, which were three elements in parallel, a voltage source connected to two resistors. These measurements came out. We see anytime elements are connected in parallel, the voltage drop across those leads is identical for each element. Of course, polarity comes into play. In the next video, we're going to recap the work we've done in example 3 and example 5 to really get a fundamental definition about series elements versus parallel elements. I'll see you in the next video.